Okay, welcome back. So if you recall, last week we talked about the linear regression. So we are building a linear a model to do a supervised task to make the inference on the labels, and the labels is a continuous variable. So today we will extend the linear models to a different supervised task, which is the classification. So the plan for today is to describe what we call the logistic regression, which is quite a misnomer. It just like historically, we call them the logistic regression, but we are not dealing with a regression task, but rather we are dealing with a classification task. So like you might recall, the difference between the regression task and the classification task is that for the classification task, we have a discrete variable. So instead of like mapping, say, to the mass of the black hole, we are trying to map things into the classes of the object, like galaxy or stars, or different types of galaxy. And just like last time, some of you might have heard of a logistic regression and might have even used them in your research. The lecture here is to give yourself the mathematical background for how we like get to the state of the logistic regression. And a logistic regression is also a very nice model to give an overview of what we call the discriminative models and the generative models. So for any like supervised task, there is always the discriminative perspective, but there's also the generative perspective. So we will see how these are linked together, like again through the lens of a Bayes theorem. But in the case of the logistic regression, these two can be quite well derived. So we can actually give a very rigorous treatment about, in what cases in the generative models will translate into a logistic regression in the discriminative models. In many cases, this is not the case, but for logistic regression, this turned out to be the case. Because of the logistic regression, we talk about we will also talk about why we cannot just treat a classification task as a regression task. Like I myself, when I was a undergraduate, I do that, right? I say, well, even I have a discrete labels, I will just treat that as a regression task. I don't care. I will just map my input into some output with my MSE loss or my chi-square. That is actually not a very good idea. So we will talk about why that is the case. And this leads to the idea of why we need something like a sigmoid function, like a tapering function. For classification, you might also have heard of terms like cross entropy loss. Both of these is actually quite widely used in a neural network. The sigmoid function is also what we call the perceptron and cross entropy loss. But for neural network, we just say we assume this to be the objective function. But this can also be derived quite rigorously through the lens of a logistic regression and a Bayes theorem. As we will see, unlike last time, which is the simpler case, for the linear regression, we have all the analytic solution, right? From the maximum likelihood estimation to the posterior of the weights, as well as the predictive distribution. They are all analytic. But in the case of classification, because we need to introduce the tapering function, this will make the objective function non-convex, and therefore we need to have some a numerical way to optimize for the models. So we will started to introduce things like the stochastic gradient descent, which also will be quite helpful when we talk about the neural network. Of course, we will start with the simple case of two classes like cats and dogs, and then we will extend that to the multi classes. So in the tutorial today, we will be focusing on the case of binary classes. But in your assignment, I think it's question number 2, you will also extend that to the multi classes. So let's get started. So as I mentioned like earlier, the main differences comparing today from last Thursday is that we are dealing with a classification task. And a classification task is still a supervised task. So given any input X, the goal is to map it into a discrete classes, right? So the number of like classes can go from 1 to K, and K can be like any like numbers. And in principle, you can get very, very large. So like at the end, we will talk about how the like multi-classes also connect to a lot of things that we are doing now with the large language models. So if you think about ChatGPT, is also a classification task. So what they do is that given the pretext, like the input, I want to predict what is the next words, and words is discrete. So let's say in English word, like in token, we have, let's say 20,000 thousands. Your goal is still to do a classification task, given the input, try to predict the next token, which is a discrete case. But for a small number of classes, the more intuitive way to think about this is to like divide the input space into some different region, right? So for example, if I have the classical like, example of a classification is dividing the classes of flowers, right? So let's say I have two features, X1 and X2, where X1 is the petal length and the S2 is the sepal length. If I just color code the classes by their color, you might see that different flower might have like different features, and that might neatly separate in the feature space. And your goal here as a classification task is try to find a boundary between them. And for a linear like models, what it means is that we are trying to find a linear separator in the feature space. And as I talked about like last time, classification is actually quite widely used in astronomy. And a large part of that is to find your survey targets, right? Because the observational resources is quite limited. So if I want to do a survey, let's say I want to do a metal poor star a survey, then I want to find pre-select stars that are in that category. And similarly, when you do a spectroscopic survey, you want to make sure that you are like observing like galaxy or star, and vice versa. You do not want to mix the other two. So your hope is that based on some crude features, without collecting the spectra, I can find the boundary between the classes, so that I can like follow up individual classes of object based on my resources. So this is a pretty typical example. So you can see that in many like cases, you would not expect the classes to linearly separate in the feature space. But if you have some like a domain knowledge, then you might be able to find the features that will separate things quite nicely in the linear space. So for example here, in order to separate the star from the galaxy, a very useful color like indices to use is the white color minus the 2 mass color. And of course, this has also like drastically changed. The one thing has changed is with Gaia, because you expect star to move and the background like the galaxy to not move. So most of the star galaxy separation also operate in the astrometric space. In fact, like this is a big like business. You know, when Gaia first happened in DR1, in the first few weeks, there are lots of like people do star galaxy like separation, and yeah. So, but this is still a very hot business beyond the logistic regression, right? So, yesterday I was talking to a candidate like student who are interested in this topic, right? So you want to separate a galaxy based on their morphology. Why? Because some of the galaxy might be more interesting than the other. So let's say you want to study like the formation of a ring, a galaxy. So you want to pre-select, you want to separate things into like ring versus not ring. And similarly, you can also like separate the galaxy images into the different Hubble like sequences. Okay, so that's sort of the motivation, but let's formulate this better. So as we mentioned, we want to have some discrete like variable. So if in the case of just two classes, the simplest way to encode the classes is just to use the value 0 and 1, right? So if I have cat and dogs, I can say like cats is class 0 and dog is class 1. But things become slightly more tricky when you go to many different classes. Like you would think if I have k classes, I might just like encode things from 0 to k. But that is not a very good idea because there is no arbitrary ordering of classes, right? Think about if I have cats, dogs, and human, which would you like define 0, 1, or 2? So if you put like something in the middle, then you're implying that, you know, so let's say I put the human in the middle, then I am assuming that dog is more similar to human than dog is to cats. And that's of course not a good idea. So this is why when we are dealing with many different classes, quite often we use what we call a one-hot encoding, meaning that if I have 5 like classes, I will denote my label to be a vector of 5 a dimension and put 1 in the classes that the object belong to. So this is of course the ground truth like labels. When you make the inference, as we will see, we will try to project x into the value y's, and y do not need to take the value 0 or 1. It can take any value between 0 and 1. And that also have a very nice interpretation. So let's say my inference output is like 0.95, 0.05, 0, 0, 0. You can interpret this as given the input, there is a 95% of chances that this belong to class 1 and 5% it belong to class 2. And this becomes like really hard if you just like encode all the classes in like 1 numbers, like 0 to k. Then it's very hard to say what is the probability it belongs to the different like classes. And one-hot encoding, as I mentioned, is also quite useful when we think about large language models, which will come back in the last lecture of these courses. So let's focus on the case of just 2 classes or binary classes. So before we jump into the logistic regression, it's always good to describe a little bit what we call a discriminative models versus what we call a generative model. So for any like regression or supervised task, there are always these 2 sides of the same coin. And they are the 2 sides of the same coin because they are linked by the Bayes theorem. So like remember last time we talked about py given x can be also be written as px given y times py divided by px. So now I have 2 types of variable. One is my input x, and one is my output classes c of k. So a discriminative models, meaning that we try to learn the one on the left-hand side. So if you read it out, it just means that I want to study given any input x, I want to find the classes c of k. And this is kind of like finding the boundary in the input space, right? So just now we talk about x1 and x2. Given any x, I try to give the classes. And this is sort of the simpler case. But there is a more difficult case that you can tackle, which is called the generative models. So the generative model say, instead of studying p of c of k given x, I want to first study P of X given C of K, meaning that given any like classes, I want to study the distribution of the feature or like inputs. And because we know that by Bayes' theorem, if I can like describe this object, then I can use Bayes' theorem to give me the output. But this is of course a much more like difficult case because the Px is generally a higher dimensional object, right? So take the images for example, X can have n pixels. So to describe the distribution of the images is much more like difficult than to describe the boundary between the images. An analogy that you can keep in mind is the following, right? So let's say I want to learn a new languages. I do not speak German or I do not speak like Portuguese, but I suspect if I have listened like enough German or Portuguese, given any new sentences, I might be able to tell apart if that sentence is German or Portuguese, because I only need to describe the boundary between the distribution. But it's much more difficult if I want to learn the languages, which is the generative models, right? So if I say I want to study P of X given P of C of K given X, I'm just saying that I just want to know the boundary between all the sentences. But if I want to study the generative models, meaning that given that I want to speak a German, I want to come out with a sentence, then essentially I am learning to talk the whole languages. But they are actually the same set of the two coins. One is more difficult than the other. And you might say, wow, if I want to do a classification, in principle, I just need to find the boundary between the distribution, right? I do not need to care about the exact shape of the distribution of the features. This is true, but when possible, like when you can do a generative models, is always like better, because once you can describe the distribution of the features, then there are a lot more things that you could do that you would not be able to do if you just know the boundary. For example, if I only know how to find the boundary of German versus Portuguese, I might not be able to detect sentences that are neither Portuguese or German. I just know where the boundary is. But if I know exactly all the German sentences and all the Portuguese sentences, then I can tell this sentence is neither a German or a Portuguese sentences. So one of the obvious application that you can have if you can describe a generative models is that you're able to detect outlier in the data. And this, of course, is very important for astronomy, which is also something that you will explore in your question 3 in assignment 3 to talk about how you can do the generative models of the quasar spectra. Now, on the one hand, you can do the classification, but you can also use that to detect the outlier. But this is really the two sides of the same coin. So like this word get used a lot like nowadays with like chat GPT. People say ChatGPT is a generative models, and the media just go on and say, we have the deep learning generative models. What do you actually mean? It's not just a word, right? It's not that you are generating, but rather what that means is that we are able to describe this term, right? So instead of just describing the boundary, we are able to describe the statistical properties of the images of the sentences. So that's sort of the an overview of what is discriminative versus generative. We will get more into details when we talk about the logistic regression. What is the connection between the generative path versus the discriminative path? By this point, I will pause a little bit and ask if you have any question. Yeah, I know my lecture is always so clear. That's great. So let's talk about the logistic regression. So as I mentioned in the beginning, this is really quite a misnomer. because we are not doing like regression, we are doing a classification. And first, we need to explain where the words logistic come from. But the regression part is just a misnomer. So let's start with the case of two classes, k equals to 2. I have the 0 class and the 1 class. And the goal here is that we will start with just finding the discriminant function. Try to find a linear boundary in the feature space that can separate class 1 from 0. The naive thing, if you have follow the lecture from last Thursday, you would say, well, I might just want to find if I want to predict the label, why not just try to do a linear models like a wu.x and call y the predicted labels. And this is what we did last time for the regression task. But this is not a good idea. In order to understand why this is not a good idea, one just need to visualize a little bit what is a linear models, right? So if I try to write down a linear models, by definition, if I have two features, my value will be a hyperplane. And what do I mean by that? So let's say I have the value x1 and x2. If I want to color code based on the value of x1 and x2, or the value of y's, then I will see a linear pattern. And this is not surprising because I know that the value of y will linearly grow with respect to both x1 and x2, right? So this is why you have some patterns. And what determine the direction of the patterns? And this is determined by your weights, right? So if I have weights that 0.12, meaning that I have y equals to 1x1 plus 2x2, then I know that my hyperplane that have all the same value of y's will be the tangential plane to the vector of the w. And if you choose a different w, then you have a different patterns, but it's always linearly growing. And how fast it grows also depends on the value of the w. And this visualization is actually very helpful to explain why you shouldn't treat a classification task just like a regression task. Because what's the problem if I just want to treat this as a linear regression? So let's say I have two classes, I have two features, x1 and x2, and I have the value 0 and 1. The optimal boundary, of course, is the one in purple. Just even by eye, you can see that this is the purple line will be the best line. But if you just treat that as a regression task, then you might risk to find the optimal solution to be the green line. Why this is the case? Because if I take the purple line, for example, I know that as I move away from the purple line, I might overshoot, right? So if the purple line means 0.5, maybe at this point, this is a value of 1. But if I move away from this line, like tangentially from the purple line, I might overshoot to be like value 2. If I then want to optimize the chi-square, then I might decided that in order to not overshoot, I should draw the green line, which is not the correct solution. Because linear models always grow tangentially to the vector, and therefore it leads to this problem. So an obvious solution to that is to say, can I not just linearly grow my function, right? Can I have a tapering function, meaning that I want all the value outside to the right-hand side of the purple line to be all 1, and all the value from to left-hand side of the purple line to be 0. So I want to have some function that will squeeze all the value from -infinity to infinity back to 0 and 1. And the obvious function to that, of course, is a sigmoid function, right? So this is just the shape of the sigmoid function, and this is the analytic form of the sigmoid function. So what the sigmoid function say is that no matter what my output or initial output or value y is, I will squash it to 1 as long as it's bigger than 1. And vice versa, if my value is like somewhat smaller than -1, I will always squash that to 0. And this seems like a very natural choice. We'll talk about why this form come to play. It's not just like some geniuses dream of some sigmoid function. Turns out that the inverse function of the sigmoid function, this is obviously an invertible function because it's monotonic. And the inverse function is what we call the logic function, which is why we have the name the logistic regression. So where does the sigmoid, this seems like a very logical like choices, but how does this come into play? Like why people know this form? In order to come up with this form, it turns out that you can, again, the only thing that you need to know for the whole courses, A is Bayes theorem, B is Bayes theorem. So if you know Bayes theorem, you can derive anything from scratch. It turns out that the sigmoid function can also like derive from the Bayes theorem. Why this is the case? Like remember, if I focus on the classes, P of C1 given X is equals to P of X given C1 times P of C1. I can also further expand the denominator because the denominator is a marginal distribution of X's. If I have two classes, I just need to sum up the two cases, right? Remember, if the chances that I bring an umbrella is equals to the chances that I bring an umbrella given that it rains times it rains versus the chances that I bring an umbrella given that it does not rain times the prior that it does not rain. Since I have two classes, then I need to only sum up two options. So if I now look at this form, if I further define what I call an odds, not what I call, what the old people call odds. So odd is just the terms inside here. So what it's asking is that what is the chances that I will observe X given that the X belong to C1 versus the chances that I observe X, the chances that it belong to C2, meaning that what is the chances that I bring an umbrella given that it rains, divided the ratio of a probability compared to the cases where I bring an umbrella when it does not rain. So this is called an odds. If I take the log of odds, then this term can be massaged into this form. Quite obviously, because I take the exponential of this term, I will get this, get back this one, and then I pull the sum of the denominator, flip that, then I will get this form, right? And this form looks very, very familiar. What this is the sigmoid function, right? So sigmoid function is just because if I want to study the log of odds of the event for two types, then the discriminant function, derived from the Bayes theorem, which just leads to a very neat form that looks like the sigmoid function. Any question? Great. But there's still one problem here because the logistic regression is making an even stronger assumption than this form. Remember, the logistic regression say, I explicitly want A to be a linear form. I want A to be WU times X. The question is, when does it happen when A can be written as a linear models? So in what assumption that I need to make for the generative models such that my discriminative models will take the form of a sigmoid function where the A here is a linear models. It turns out that if you make a very strong assumption, this turned out to be true. So if I further assume that given any classes, my distribution of X, this should be a vector X, so this is a typo. If I say the distribution of all the feature X given the classes is a Gaussian. Moreover, all the classes have the same Gaussian with the same covariances, but they are only differ by a shift in the mean of the distribution. If this assumption is true, then you can just do some massaging and get to this form. It's quite clear because this is an exponential term. If you take the log and all this yada yada, the reason that you need the covariances to be the same for all the classes is because you want the quadratic term to cancel out. If that is the case, then you will see that this can be A of X can be written as AX plus B. Meaning that if I make this assumption, then the things that inside the sigmoid function turn out to be a linear models. Great, voila. To recap, right? So we say in the logistic regression, essentially the assumption that you're making is the likelihood of the data, the feature space given the classes always form a Gaussian and they have the same width. Then I can this will translate into exactly the logistic regression models where the classes can be linearly separated with a linear boundary in the feature space. And of course, so far we have only the derived P of C1 given X, but given that we have only two classes, P of C2 is just 1 minus the first term. If this seems like too much math, the thing that you should keep in mind is only the following, right? So let's say I have two features, X1 and X2. I have two classes, the blue and the yellow. And if it turns out that given the classes yellow, the distribution of X1 and X2 is a Gaussian, and the same Gaussian applied to the blue one, then this generative models will translate into a logistic regression where the boundary can be found with a linear models. This is a particularly important one because you need to sort of understand when you run a logistic regression, what is the assumption that you are making, right? It's just not like you just run sklearn and say it does not work and then just move on, right? So knowing that what do not work and what is the underlying what we call the inductive biases of the models will help you to find a better models. You might say, well, this seems like a very strong assumption, right? When do I expect the feature itself given any classes all have the same covariances? This seems very odd. Like if I want to describe the distribution of the sentences in German, most likely it will not have the same width distribution as the Portuguese, right? Similarly, if you think about the flower cases, it seems very odd. So let me go back, right? So if I go back to this cases, it's very odd that to make assumption the distribution of the pink line, the pink dots, the green, the yellow dots, and the blue dot all have the same covariances, which is not even true for these cases, right? This is, of course, a very strong assumption, but it's still a very powerful models. Let me go back to where we were. One more. This is still a very powerful models, just like in the, and this is because, just like in the case of the linear regression, you are not tied to use the input X. You can always first project X into phi of X. So let's say just now in the flower case, it might not be exactly the same covariances in the petal length and the sepal length, but you can maybe come up with some feature that this turned out to be true, right? So of course, I can do 2 times the petal length or the petal length square, right? In that case, you might be able to linearize your features such that this assumption to be true. Still, you might say, well, I'm really lazy. I do not really want to think about that. Good for you. Most of the time, you do not need to think about that, right? So the problem with the logistic regression is the feature, just like the linear regression. But in many cases, we do not need to come up with the feature like ourselves. So from next week onward, we will talk about some of the methods that can get rid of the needs to define the features. One of that is the neural network. So you can think about the neural network is learning the features by itself. Or you can use, we call the Gaussian process, meaning that instead of defining the features, I only need to define the similarity between the objects. This is called the kernel traits. And these two approaches actually extend beyond the linear models and give you a more enriched dictionary to do the supervised task. And this is why for any machine learning courses, we always start with the linear regression, because once you understand the limitation of the linear regression, yet it's still like very powerful. As I mentioned, more than 80% or more of the job out there is done by a linear regression. But once you know the limitation, then you can start to see why you need K-pop or like your classical or like music, right? So once you know how to play piano, right? Okay, so we are doing some linear separation. Like this is another way to look at this. So if I have two classes in X1 and X2, and in X1 and X2, the blue and the yellow classes distributed in this way, then of course it's very hard to find a linear separator that separates the two classes. In fact, it does not exist a linear separator that separates the two. But luckily, you do not need to deal with X1 and X2. Obviously here, if you define the 0 point to be the center, you will find that all the yellow point is within some radius, and all the blue points within the closer radii, right? So therefore, if you can transform your X1 and X2 into some new feature space, phi of X, then it might be linearly separable in that space. So feature engineering is a big part of machine learning, especially in the old day of machine learning, which is also a very fun thing because in before deep learning, a lot of machine learning is about feature and engineering. So you think about neuroscience, right? So in the past, people require a lot of domain knowledge to find the features so that you can use classical models like the logistic regression or linear regression to understand the task. But because of deep learning, this seems to be slightly out of fashion now, because you can learn the feature from the data when you have a lot of data. There is always this debate how much you want to include the features, and this is completely tangential to what we need to talk about today. But for example, this is tangential note. I didn't verify that, but I have heard that say in Neuralink, like the Elon Musk brain thingy, they are hiring people who do the neuroscience. They have no background in biology, because they believe that with enough computational power and data, you can learn the feature all from the data. This might not be true for astronomy. So my position here is because astronomy is still quite expensive to get the data, especially the simulation. So if you can engineer the feature based on your knowledge, is always better. And this always, we talked about last time, there's no such thing as pure modeling or pure learning. If you have infinite data, let's say with large language models, then you can get rid of the modeling. You can just learn all the features. But if you have not enough data, then you want to focus on more the domain insights. Right. So full of thoughts, right? So another thing that is tangential to the courses today, but just good to know. So one thing that is really exciting, especially what my group has been doing, is to say, I want to have a generative models, but assuming that the features exactly have the same covariances seems completely dumb. This is not true in most of the cases. But one of the very exciting things that has happened in the last 5 years is there are lots of ways that deep learning seems to be able to understand the distribution of things in the very high dimensional space. And this can be easily understood, right? If you play with like Midjourney, or since last weekend, like DALL-E 3, then you know that they are able to generate the images or sentences, or means that they actually understand how to do the hard one, the P of X given C of K. And that actually like opened up a lot of things that we couldn't do in astronomy in the past. In the past, we are always like dealing with feature and engineering. But now suddenly, if you can generalize the generative models, then you can do a lot of sciences that you couldn't do, and which is also like maybe like 50% of my research group now is like extending this. But it's good to start with the basic, talk about the logistic regression and how these two things come together. And this term become quite popular, like the thing that I just like described. Now in astronomy is called the simulation-based inferences, or SBI. Like 2 years ago, it's called LFI, but now people use SBI. So LFI stands for like likelihood-free inferences, which is also a misnomer because nothing is likelihood-free. You are doing like Bayesian statistics. You have a likelihood, right? Just that you do not need to parameterize the likelihood. Anyway, that's all the digression, just for general knowledge. Let's come back to the logistic regression, right? So we have like described the origin of the logistic regression, but we still need to define what is the objective function that we should optimize. Again, the only thing that you need to know is Bayes' theorem, right? So how do I find the best boundary? Recall, the gist of Bayesian statistics is to say, of course, I do not know what is the correct like boundary, but I can propose what would be the boundary and see if given the assumption, whether or not I can maximize the chances of observing what I observe. That's called the likelihood. So what I observe, we observe X and T, right? So X is the input of your training data, and T is the ground truth labels. And I want to find the best W to optimize the chances of observing what I observe, right? So if Tn is equals to 1, meaning that the object, the nth object really like belong to class 1, what is the chances that I will observe Xn? Oh, what's the chances that given X I will observe the class of C1? And this is what we have just derived, right? So under the assumption of the logistic regression, P of C1 given Xn is just this term, the sigmoid of the linear boundary, right? Importantly, the W here is not a fixed value. This is my proposed like value. For different proposal, I will have different likelihood for this like data. I want to optimize my W such that I optimizes the likelihood of observing this ensemble of data. So this, of course, in the case of Tn equals to 1, if Tn equals to 0, class 2, then it's just 1 minus this term. And this is the likelihood of observing this one data point. But I have a bunch of the data point, right? So I want to optimize the product of the likelihood. Just like in the linear regression, if I can write down the likelihood for one data point, I can write down the likelihood of all the data points by taking the product of all the likelihood, right? The chances that I have eaten at McDonald's, which I also did like today because I have no time, versus it rained today is the product of the two, because they are somewhat like independent. Even though they are not exactly, but in this case, it's somewhat independent. So I just want to write down the products of all my data points. So I do the product of n equals to 1 to n. There is a very compact form to write down the joint likelihood, right? So remember we say if Tn takes the value of 1, I will take the value of Yn. If Tn is equals to 0, I will take the value of 1 minus Yn. So I can actually write down in this very compact form, because if Tn is equals to 1, then the term on the one on the right hand side here drops. So I just have Yn. if Tn is equals to 0, then the 1 here drops. Then I have 1 minus Yn. So like written in this form, give me the product of Yn or 1 minus Yn depending on the T of n. So this is just a very handy way to say, given any proposed like W, this is my likelihood. And my goal here in the maximum likelihood sense is to find the W that will optimize this. Right. So one catch here, right? So here, for the simplicity for today, we will not go to full Bayesian, meaning that we are only finding the best like W. So if you remember from last time, when we talk about the linear regression, not only we want to find the W, we want to find the distribution of the W. Do not worry, like we will come back to that point when we talk about the Gaussian process. We'll talk about how to treat the logistic regression in the Bayesian sense. But anyway, so for now, we will just want to find the best boundary. And the term that we just write down is also leads to the famous cross entropy terms, right? So just like in any machine learning, if I take the power of something, it's always very hard to optimize that objective function. So it's good to take the log of the objective function because it will make things in this, because the loss function can have orders of magnitude in differences in the value. So if you take the log, and log is still a monotonic function, you do not change the optimal point, but it will make things more numerically stable. One more thing, because we want to maximize the likelihood, if I take the log, I still need to maximize the log of the likelihood. But if you remember, for most of the packages that we have, like SciPy, we only minimize the thing. So instead of optimizing the log of a likelihood, we will minimize the minus the log of the likelihood. So just now we have y of yn to the power tn times 1 minus yn times 1 to tn. If I take log of that, then I will get to this term, right? So the product become the sum. Yeah, actually there should be a big bracket here, so another typo. So this is just tn times log of yn. And this is a very familiar term that what we call the cross entropy. So nothing is magic here. Cross entropy do not just fall from, I don't know, like Gibbs, right? It's just like some god and say, you should use cross entropy. Nothing is given, just that we want to optimize the likelihood of observing what we observe based on the proposal that we make on the models. There's one problem here, right? So the yn itself, remember, this is a short form for sigmoid of w's times xn. And sigmoid function is obviously a nonlinear function. So the whole things here are nonlinear, right? And there's also no guarantee that this is convex. Pretty sure this is non-convex, but I need to check that. So meaning that you cannot find an analytic solution. You cannot just say, I can have an analytic form for the optimal point for the loss function. So this is the part where you start to need to use some numerical tool to find the solution. There are different ways to do to find the optimal point. The lazy one is to use SciPy. Who cares? You can use SciPy to optimize that. Usually it works, but it's also good to introduce a gradient descent. SciPy also use gradient descent for some of the algorithm. So gradient descent is actually a very simple method. So what is gradient descent? Gradient descent just say, let's say I have some function and I want to optimize the function. I do not know how to solve analytically, but how do I find the optimal point? The simplest way to do that is to take the negative steps based on the gradient, meaning that I will propose some initial a W, but I always walk in the negative direction of the gradient. And that will give me to some optimal point that might not be a global minimum, but it will give me some local minimum. So the visual way to think about this is the following. I didn't draw this, Joe draw this. So you have some function f, depends on x, and you do not know how to find the minimum point. But do not worry, if I can start with any point, each time I take df dx, take the negative steps and then just roll down. And how fast I should take the step, of course, is a choice. So this comes back to the hyperparameter here called the eta. And this is, of course, something that you need to tune, because if you take too big a step, right, poof, you overshoot. But if I take too small steps, then it will take forever to get to the minimum point. But there's still one problem here, right? So remember, the loss function that we have are the product of the likelihood, turn out to be the sum of the likelihood. Then if I have, say, a training set of 1 billion like data point, then I'm doing sum of 1 billion operation, which is, of course, a very expensive one. If I want to, each time I take a step, I need to do 1 billion operation. That will take forever for me to get to the minimum point. So what we call the SGD, the stochastic gradient descent, is just to say, instead of calculating the sum from n equals to 1 to big N, I will just take a subset of that. So I assume that if I randomly subsample from my training data, then I will still get a representative gradient of the loss function. This is much faster because then you can take more steps and get to the minimum. But there's actually more than just like cheating, right? One of the main reasons that why SGD is very useful is because, remember, right, if I take, strictly speaking, the total gradient, meaning that I take the E of W summing n equals to 1 to big N, if I take a very small steps, I am guaranteed to fall into a local minimum, which is not what I want, right? So sometimes I have a landscape that is more jagged. I want to have some randomness to be able to not stuck in the local minimum. And this is also why the SGD is very powerful, because it gives you, and this is where the stochastic part comes from, because even for the different subset of data, your gradient might not be exactly the same. So this gives you some random noise that might help you to get out of the local minimum. There is a lot more than what I just say. This is exactly a field that you can denote your career and win a Turing prize. There are lots of why the stochastic gradient descent. We stumble on that. It seems like a very blind and naive methods, but it's mathematically very beautiful. And there are reasons why deep learning works. There are lots of things that are tied to the SGD. But for practical reason, getting about just rolling down the hill. And for logistic regression, this also have a added benefit. Remember, right? So this is the objective function that we try to optimize. If I want to take the gradient descent, by definition, I need the gradient. Luckily for this loss function, the gradient is actually analytic. So even the optimal point for the W is not analytic, but DEDW is analytic. So here you need to unpack a little bit. It's like, where is W here, right? There's no W here. That is because we write Yn as sigmoid of X times the W, right? So this should be written as the sigmoid of something. So if I do DEDW, if I do the chain law, then I have D sigma DW. And it turns out that D sigma DW, you can prove that this is true. So D sigma DW is just the sigmoid of these terms, which give you, if you do some high school calculus, it leads to this point where the gradient of W is completely analytic. That depends only on X, T, and Y. And all these are things that you would need to calculate anyway. So you get the gradient for free. In practice, this is not a big deal. So as we'll see in 2 lectures, when we talk about neural network and autodiff, all function is differentiable, right? You just need to algorithmically do that. But in this case, there is a closed form that you can write down. So this is basically what you need to make a lot of money. So the master algorithm of machine learning can do 90% of the jobs. Basically go as follow. Your supervisor give you a task. You say, oh shit, okay, I will first come up with some features and some label, try logistic regression. 90% of the time, like this will work, done. And then if if it not do not work, repeat, find another features, and then do the logistic regression, and hopefully done. If you try a few times, it does not work, then you might want to do neural network or Gaussian process and yada yada. Right. Cool. Any question? Okay, so let's talk about the last part, which is extending this to multiple classes. And this is also what you need for assignment 3, I think question 2. So we just talked about the binary cases. I have 2 cases, but of course in many scenario we have more than just 2 cases. So we need to extend that to the multiple cases. So from the beginning we talk about why we use what we call one-hot embedding, because there's no natural ordering of your classes. So you might, instead of just encoding your classes to be a scalar, you will use a vector with the same dimension of your classes to denote the probability of getting the certain classes. So the extension is actually quite straightforward. So remember how we get the sigmoid function. We get the sigmoid function because we write down, even though we just want to get the discriminant function, we can use the Bayes theorem to write down in the generative models. And for the multiple classes, this is exactly the same, except now you have more than 2 classes. So instead of just summing class 1 and class 2, you will summing up all the class J. And now we will define the A, instead of the log of odds, I will just use the denominator, right? So I will define A of k to be sort of the likelihood, right? So the chances of observing X given the classes C of k. This is something that I do not know. So this is something that I want to optimize. But since I'm dealing with different AK for different classes CK, one differences compared to the binary cases is that we need more than just one boundary, right? So in 2 classes, it's very easy to see. So since we are dealing with a linear models, so the WU here has the same dimension as X. So if I have X1 and X2, if I just want to have 2 classes, I just need to draw one line, and the one line have 2 degree of freedom to separate the 2 classes. But I cannot do that if I have more than 2 classes, right? Even I have 3 classes, I might need 3 lines, which is, I think it's the Mercedes, a Mercedes Benz, right? So you have the sign. If I have 3 classes, then I need to draw 3 lines to separate the 3 classes. If you have 4 groups, then you have Audi. Anyway, so you can see that the AK here, for different AK, you have a different WK, meaning that the degree of freedom now is not just n of x, but m times n of x, k times m of x. So I have k line. If I just use this definition, then I will just get back to this form, right? So this is just the exponential of the denominator and the denominator. And this thing is what we call the softmax function. Again, machine learning people love to give you a lot of suitcase word, meaning that give you a lot of words that just you feel like you are looks like very grandiose, which is a big problem in machine learning because they come up with new words all the time. Sometimes it's even worse in Astro-Stats because people redefine things that have been defined and use the different words and then call that all the different things, which is crazy because this thing all come in 1950 or 60. So softmax function is where it come from, right? So again, come from the fact that even though I want to describe a discriminant function, this comes from the Bayes theorem, and therefore we get the softmax function. This is a particularly nice function because if I sum up all the probability of C of k, then my nominator will be the same as the denominator. So it will sum up to be 1. So all my output will sum up to be 1. Therefore, it can be like interpreted as of the probability of belonging to a certain classes. Right. So again, so this is the output, right? Y of ik. Slightly more tricky because instead of just yi, we have yi and k. Because for any example I need to predict what is the chances that it belong to class K. And because K is this is a RK like vector, where the individual like entry here show you the probability that I belong to the class K. Okay, so you say, what is the function that I need to optimize? Again, the only thing that you need to know is Bayes' theorem, right? So you want to optimize the chances that you observe what you observe. So what is the chances that you observe given X? What is the chances that this belong to T of K? It belongs to the TIK. So remember, for any T of I, there's only one value of K where this is non-zero, because you are doing a one-hot like embedding. So you know the ground truth like label. You have only one value here is non-zero. And the likelihood that belong to T of ik is exactly Y of ik. But because we are taking the log of the likelihood, so you get like these terms, right? This is also just a very compact form to write things down, because again, for even though you're summing up, another type, no, this is correct. I'm summing up all the sample from I1 sample to the N sample. But for any terms here, for any given I, there's only one term here is non-zero, which is the correct classes that belong to the one-hot like embedding. So this is just a natural like extension of the binary like cases. If this seems a bit not clear, you will just go back to think about how to deal with the binary like cases, and this will extend to the different classes. So our goal here is to find the best set of the WU that will minimize the minus of the log of the likelihood. Okay. One thing though, right? So just now we talk about, think about yk. So this is a vector of k dimension. You can take like any value. So even though the ground truth like label is like 0, 1, 0, 0, 0, 0, 0, yk can take like any value, just that the sum of that is 1. So let's say my yik, like my yi is like 0.95, 0.05, 0.0000. So what should I declare the classes of this object? The simplest thing you could do is to take the maximum like value, right? So if I have yik, the maximum k is the first like classes. I will define this to be the first, this object like belong to class 1. But this is actually not that clear cut, because in many cases you want to be more conservative, right? Give you one example why, like in some cases you want to be more conservative. So let's say I am testing for cancer, and your doctor say you have 95% that you don't have cancer, you have 5% that you might have like cancer. You might not just want to go home and say, wow, I have 95%, I don't have like cancer, hooray! I define myself to be non-cancerous, because that part you cannot tolerate false negative, right? So even though you have the yik, how to project yik into the classes is a decision that you have to make. And quite often it depends on what we call the confusion like matrix, meaning that for any like decision, for any ground truth like labels, you can always like project into what is the classes that you would predict on your test set. We talk about the separation between the training and the test set. In some cases, you do not want to like tolerate the false positive, and in some cases, you do not want to tolerate the false negative. It depends on the cases. You need to draw the boundary, and this is something that you will also like explore that in your assignment tree. And another thing that you want to do is, in many cases, your training sample is completely skewed, right? So if I want to find a boundary for like non-cancerous and cancerous people. Of course, there are many more non-cancerous people. Remember, the sum of the likelihood is very democratic, right? So this is taking the mean of all the likelihood, meaning that if you just like naively draw the boundary, giving equal weight, then you would, of course, want to please the majority. But this is something that you might not want, because this might give you a lot more false a negative. So even the loss function itself like can be tweaked, meaning that you might say, instead of this thing, if for a given like classes T of I is very rare, I want to give a higher weight to that classes. And again, like this is totally an art, not a science. It's just that what like decision that you want to make. But still, all this like come from first principle. Just that in some cases, in the like in the decision, you need to make clear what you want. So you might want to change the weight, which is also something that you will. Yeah, I misspell that. I always like the weight is always like a bit strange for me. Anyway, this is something that like you would like also explore in assignment 3. And another big classes of like research is your absentee vote, right? In some cases, you just say, I do not know if you are cancerous or not, do another test, right? So this is another way to deal with the boundary. This is still a very active field of research. This paper come out in June of this year. Largely, I just make aware of this work in a recent conference. So this is something called the conservative prediction on confidence minimization, meaning that you should only vote when you are really confident. Anyway, so what we have learned today. So we started with extending the linear models from regression to classification, and this is what we call the logistic regression. And a logistic regression is really a very nice springboard to understand the interplay between the generative models and the discriminative models. Even though like logistic regression by definition is finding a discriminant function, we show that this is equivalent of having a generative models where the covariances are exactly the same for all the classes. We talk about the origin of the sigmoid function. It comes from log of odds, and this traces back to the Bayes theorem. We talk about the cross entropy. How does that come from? This is just maximizing the likelihood of having observed what you observe. And then since we have a sigmoid function to have a tapering function, we make this function non-linear. So it requires some numerical tools. So we talk about the gradient descent to find an optimization function. And then we have extend this to multiple classes. We will then talk a little bit on the tutorial side because we still have like 20 minutes, but I want to pause a little bit to ask if you have any question. Yeah.
The logistic functions logic is derived from limitations. Why is it not used exclusively? I mean, there are or even in the probability function, there are other functions.
Okay. So there, so just repeat question. Is there people online? I'm not sure, but yeah, but we will like repeat. So the question is, if the logistic regression is there's a rigorous like origin with a Bayesian, why not we just use the logistic regression, and why we also just use sigmoid function but not like ReLU? Because if you think about like neural network, like you always teach with like sigmoid function, but then you just say, oh, you know, it does not work that well, move on. So there are two parts here, right? So the first part is logistic regression is not so the Bayesian is the core of like everything, but we talk about the logistic regression. If you think about in the terms of the Bayesian inference, is making a very strong assumption on the distribution of the generative models. Particularly, you're assuming that the covariances given any like classes are exactly the same. And this might be true if you can like feature engineer things in, in fine-grained like details. But in many cases, this might not be that easily true. And it might not be even true. Right? So there might not be a very obvious or any basis function, but you can, strictly speaking, if you are continuous, there always like exists some function that will like distort thing in the way that you want. But in many cases, this is too strong an assumption. The sigmoid function and ReLU is completely different. So the sigmoid function, this is why when people think about like neural network, people start with the sigmoid function. But we will talk about that in the neural network. The problem with the sigmoid function is, I'm trying not to blind you with all the slides. So the sigmoid function is like this way, right? And the problem here is that if you want to do a neural network, you want to do a gradient descent. And the sigmoid function have a very pathological like gradient, meaning that in some cases, the gradient get more and more like shallow. It does not like decisive like enough to say, I do not want to go there. So you will just like prime yourself into a loops that you will be stuck in some point for a long time. And the reason that people do the ReLU or all this function, a large part of that is just because the gradient itself is more numerically like stable. So it become like a proxy for many things. But if you think about a neural network, there's no reason to use like sigmoid function to begin with, because even though that is sort of the Bayesian viewpoint of the neural network, but the concept, the preconception of the neural network is not require the Bayesian treatment. So what you really need is a nonlinear function, and there's no reason that you want to just start with a nonlinear function with a pathological gradient. Passion. Okay. We have 15 minutes. Not sure how. So luckily I'm also a bit tired today, so I'm not sure I want to do live coding, but we'll walk you through the tutorial. I can also try if I have time. Just slept too little. Okay, so let's walk about what is the tutorial about. So give some context. So this is another cases where classification is very important. This is again like 5 lines of code in my coding. I think that this is like 5 years old. It's either like 60 to 70 times now. It's a very simple paper. So the context here is in the Milky Way, quite often you want to find the red clump star. So what is the red clump star? Like if you remember your stellar like astrophysics, you go from the main sequence and then to the giant branch. So when you go to the giant branch is hydrogen shell burning. You go to the tip of the red giant branch, then you fall back to become core helium burning. So the red clump star is also known as the core helium burning star. And they are very nice because for some cosmic miracle that the core helium burning star tend to have the same light brightness. So they're basically the type 1a supernova for stars. And for standard candles, it's very useful because if you know there are standard candles, just based on how bright they are, you can know their distances. And therefore you can get a very precise distances, like down to about like, I think red clump can get you about 3 to 5% in distances. But there's a catch, right? So turns out that the cosmic like miracle like do not work extremely well because the cosmic god still make a jokes on you because the temperature and the gravity of the red clump star tend to overlap with part of the red giant branch. Like, what the hell? Why do you want to like have the same temperature, right? But the red giant branch, despite they could have the same like temperature and gravity, they are not standard candle. So if you mislab some of the red giant branch, the distance that arrow can be like 20%. So there has been a need, right, to really just use some feature, either the temperature or the gravity or the photometry, to find out where is the red clump star like versus the RGB star. And before our work, classically, the people just draw a box, right? Just draw a box and then say red clump star, all right? Turns out that you can do slightly like better, like even with a few lines of code. Here we actually use the neural network, but it's the same idea. So even like a logistic or a regression would have gotten you maybe like 95 or 99% of the performance. So I want to find a linear boundary that separate out the red clumps from the RGB star. So that's sort of the question. Let me walk you through a little bit. So the goal here is to say, well, if I look at, this is a high quality data, so this is somewhat like cheating. So if I have the temperature and the gravity, if I have very precise measurement for them, so let's say from the Gala spectra, then your temperature and gravity is good enough that you can mostly like separate out. And where does the ground truth labels come from? The ground truth labels come from astro-seismology. So in principle, if you can observe a star long enough, you can look at the pulsation of the star to decide if they are red clumps or the RGB star. But those are very expensive like observations. So ideally, you want to use simpler like feature like temperature and gravity to separate out the two. So the labels here come from like astro-seismology, and your goal here is to find a linear boundary. It's true that in this high quality, like technically you can draw a line, but you do not need to do that. You can just write a few lines of code. And the optimal goal is to find the boundary, right? So this is the optimal like boundary that will separate the one left from the right. And we will show how we do that. A lot of code here are actually quite redundant because we code up the stochastic gradient descent. In principle, you can just use a SciPy like optimization to do that. And there is a added niceness of that, which is, like remember when we have a linear models, we have y equals to sigma times x dot the w. If I normalize my x, meaning that my x value all have the same range, because sometimes your x could be like different range, right? So in this case, the temperature can be few thousand Kelvin, and your log G can be just order of 1. But if you normalize that, then you can use the vector like W to tell you which feature is important, right? So the larger the value, the W corresponding to a certain label means that you are doing that with more of that features. And this is exactly what we're showing you here. If you just use the temperature and gravity, like we will not do as good a job. We also include the metallicity. We also include a lot of like redundant stuff, which is fine. Just like include RA and DAC and the photometric. You expect those have no influence, right? If this has a very high value, then you are doing something wrong. Or somehow the red clump star decided to be part of the sky, but not the other part of the sky, which is unlikely. So this is a good check. So once you optimize that, you can just like visualize the value of like W, and this is what you expect. The log G play a big role, the temperature play a also big role, and metallicity play a slightly a smaller role in determining the cluster. And the rest is pretty straightforward. We also have, we didn't talk about the regularization. So just like linear regression, if you do with the Bayesian version, you can also include a separate loss. So beside the cross entropy loss, you can also add lambda over 2 divided by the omega square. Remember, what do we do? Like, why do we do that in the linear regression? Because if you have this, you can either treat this as the prior, a Gaussian prior of your likelihood, or you can just say, in the more machine learning hand wavy way, I want to penalize whenever I use a new weight, it better do something. Else I would prefer to have a 0 weight. And the rest is just straightforward. I have 10 minutes. Let's see how much I want to. I totally didn't prepare this part. Let me try to see if I can do that on the fly. If not, just think about this is a comedy show for the last 10 minutes. Yeah. Okay, so this is the data. So I will load the data. Whoa, shit. Okay. Let's enlarge this. X dot shape. I think this is 8 dimension. Yeah, let's not take all eight dimension because I know like yeah, let's make it like simpler. So just take the important like features. So let's just take the temperature and the or the gravity, right? The plot hold it with T. Yeah, that's correct. Yeah, so we get the value here. So this is the temperature and the gravity. Normalize X. So there's a technical term called the Whiten data. Subtract the mean, like divided by the covariances. Now, if I make the same plot, it will be in the same range. Not like instead of like a few thousand and like order of one. Now I have all in the same order. Define logistic. I probably need to set my function. Define the sigma function. Define cross entropy. So as long as you know what is the math, it is quite straightforward, right? So y and t, this is correct, like t times log of y minus t prime log of I. Optimize that with SciPy minimums. I have a function x and t. You think a little bit. So I will like initialize w. Is it good to initialize with 0? Let's try that. I probably do like a Gaussian, so minimize that. Gradient losses. Have I defined loss? This is very strange. I shouldn't. Okay, let's try. This would not run. Define the loss function. Yeah, weight and x and t. Probably just read. I will use the x and the w pass through the sigmoid to define y, and then I will calculate the cross the entropy loss with y and t, right? And then I do not want like gradient. Can I just do something really simple? Yeah, I mean like since we have the gradient, it's much like easy, but I will just LFBGT probably need like gradient without the need of gradient. Forgot which one I do not need BFGS. I do not need that. Ugh. Can I just do something? If I just not do that, optimize. Let's see if it runs. I'm not sure if this will require gradient fits. Okay. Probably need like gradient. Sigmoid function. It's complain about this thing. It's very strange. So this does not run. This is a 0 point, right? We just do 0. You know what? Because here I'm defining the bias. I remember we have the bias term ax plus b. So I need to extend that, right? So could extend data with the bias 1. Yeah, so I need to concatenate 1. So in this, and then optimize. So you do not like that, but this should be fine. No. We like transpose. I hate you. Why am I doing this? What is the shape of this? Okay. I'm pi 0. Right. Wait, what is 4? Are you kidding? Wait. X dot shape. This is dumb. Okay. Cool. Hey. Ew. Predict predict the classes. Go away. I do not need you. I'm cheating because I forgot to separate the training and the test set, but it's okay. It's a low degree of freedom. This is too lazy. Come on, I do need to define a function. Sure, if you want. Predict the classes. So remember, like, given y, you still need to like decide how you define the classes, right? So predict the max, right? It's okay. I plot the prediction first. So y can take like any value like between like 0 and 1. So I will just try to scatter t and y. This is probably y is some weird dimension. What is the y shape? Wait, where's the shape? You do not like this again. Why? Because why do you always do this to me? Go away. Don't need you. Go away. Ooh. T and y. Does not look very good. Okay. Optimize this thing, but more or less looks okay. Like 1, it go mostly to 1, but there's something is not exactly right. Let me plot the scatter plot. Let me plot the x data, but now color code with y. Yeah, see there is a boundary. Great, done. All right, so you can do slightly better. So the reason that I do slightly better because I include the metallicity. So let's try this. If I do a metallicity instead of doing just take also the metallicity. So I have temperature, gravity, and metallicity, right? So if I just go through sigma, go away, result. Oh, not good. Something is going wrong. Let's see. Let's see, is it doing better? Okay, something is not right here. It does not like my metallicity. Why does not like my metallicity? Cool. Cannot figure out. This is correct. Classes. X mean. Oh, did I not subtract just now? Oh, okay. Because maybe there's some invalid value. The easiest thing is to use the panda frame and drop the duplicates and drop NaN. I don't think I include NaN though. But it's 230. Good, done. So so I have kind of done the simpler like cases. So remember the main thing here I want to show is that you can easily write down a very short code if you use the SciPy optimization. In the tutorial, I use a more gradient descent, which might or might not be like necessary. Right. Cool. So I'll see you in 2 days. Bye-bye.